Good morning. So, today we will continue our discussion on power amplifier. So, let us have a quick recap on what we have discussed last day. So, in power amplifier, we will be discussing different classifications of amplifiers, and these classifications are based on the fraction of the cycle of input sine wave the transistor is conducting. And we are having class A, class B, class AB and class C. In this chapter we will be discussing A, B and AB. C we will just introduce, but we will not discuss in details. So, if we start with class A we already have studied, that is our common collector or emitter follower, that we will see. But the problem of class A is its power inefficiency. Next type, so we will be seeing that why we are going from A to B and then from to AB and then why to C. So, you can understand that one important factor is power efficiency. Okay. So, here the efficiency is maximum and here the efficiency is minimum, okay, that we will check. So, this is one reason. So, B type is, so this is common collector, this is push pull type of circuit, that we will see. Now, while this discussing this power amplifier, as this is used in the output stage and large power is this is associated, we need to be careful about the thermal characteristics, because large temperature can destroy the circuit. So, as it is used in the output stage, one important requirement is that low output resistance, so that it can deliver the output signal to the load without any loss. If we are having some output resistance, there will be loss, right. So, if it is low, that is added advantage, that we will check. Generally, as the output swing is large, so small signal approximation is not useful, and for linearity another term is useful, that is called the total harmonic distortion. From the name total you can understand this is a summation of all the harmonics, and it is generally expressed as a ratio to the all the harmonics power to the fundamental power, okay, percentage of the RMS of the fundamental. That means, or in dB you can say summation of all the harmonics minus the signal, signal means fundamental main frequency. Okay. So, if you have very low THD, that means your distortion or is will be less, your quality of signal will be better. Okay. And by the mean of high power, we want to say that it is greater than 1 watt or so. So, these are the points that we discussed last day. And another reason that we want high power efficiency is that if it is driven by any battery supply, its battery life should be prolonged, and another is the temperature dissipation will be less. So, that is the definition that we also discussed last day. Suppose you have a MOSFET or you have a BJT and you want to, for all condition you want to be it on, this signal will be connected here, right. So, along with this signal you will be also having the DC biasing superimposed, right. So, you want to ensure that there is a certain DC value, on top of that DC value you are having the AC signal. Why you want to do that? So, that for the full time it is on, right. So, class A you see it is having a DC current, we are expressing with collector current IC, but same you can express with VBE also, right. So, VB you can say DC plus AC, so it should be always on. So, similarly if it is having a DC base voltage, so correspondingly it will have a DC collector current. On top of that DC collector current, it will be having an AC variation based on the signal variation, right. So, this is the definition or classification of class A, that the transistor is for the full cycle it is on, from 0 degree to 360 degree it is on. Class B, the main transistor is on for half of the time. So, you need another transistor to work for the another half of the time. So, it will be like this, one transistor is operating at positive half and another transistor is operating at the negative half. So, that is why the terminology push pull amplifier. So, class B we saw that there is a problem during the 0 crossover. For a small fraction of time both the transistor are off. So, I need to deliver the current so that the output load voltage looks like that input sine wave, right. What is my job? My job, I am giving a small signal and I need an amplified replica. That is the job of the amplifier, right. So, to do that, the moment this input sine is above 0, I need to deliver that current, and also when this input sine wave is below 0, during that time also I need to deliver current to the output load. Now, in class B what we find that at the 0 crossing both the transistor are off. So, there is nothing to deliver the current. So, output current at the fraction it goes to 0. So, now you see if you compare these two sine wave, they are having distortion, right. It is not like the exact replica of the original sine wave, or you can say that the THD will be more, harmonic distortion will be more, right, and that is happening at which point? 0 crossing. So, this is 0 crossover distortion. So, this was unwanted in which case? Class B. So, in class AB little bit modification is done, that in class B our DC was 0, right. You see it started from only 0. So, it is only AC signal or signal, only the signal. This biasing will not be there. In case of class B, this biasing will not be there, it will be directly connected to the signal. Okay. So, in this case a little modification is done. So, a little DC is added, small DC, so that only at the 0 that was off I need to make it on. I am not adding a very large DC like this. See, this is quite large. So, that this IC, this DC should be at least this minus IP, this DC should be at least larger than this negative peak, otherwise what will happen? This will go off. But in this case we are adding only a small portion of DC, so that at the crossover, you see this is the 0 crossover, that time it should be on, and its conduction angle is just greater than pi, but much less than 360 degree 2 pi. Okay. And remaining is class C, that is you see its conduction angle is even lesser than pi. So, if you see that maybe it will be on for this period. Okay. So, it is on for a fraction of pi. So, these are the classifications of 4 different type of amplifier. So, we will be seeing that what are the implications of different amplifiers. This class C amplifier are generally used in radio frequency amplification. Okay. For example, they are used in mobile phone, radio and TV transmitters. So, all your mobile phones, they are having class C type of power amplifier. Okay. They use some tune resonator oscillator circuit, that the tank circuit that we studied in the oscillator, those kind of tank circuit are used at the load. So, although we will be defining most of the things with BJT, because BJT has more power driving capability and more robust, but nowadays MOSFETs are also used. So, we will be seeing that in class A category we have already discussed those. So, let us see this. So, this is our circuit. So, can you tell me which is signal and which is DC? I have two BJTs, right, one is Q1, one is Q2. Signal is connected to which of the BJT? Q1, right. Why? We discussed about the nomenclature, right. So, you see the input is italics and small, subscript capital. So, this is the meaning of which type of signal? AC signal, right. So, AC means this is our signal. If we used a capital nomenclature like this is our DC power supply, right. We discussed about this nomenclature. So, where you will be seeing VI or Vsig, so you will be understanding that this is my signal, that signal you want to amplify. So, which one is your main driver? This is your main driver. This one, what is this? Why this is added? This is added to provide the biasing. This potential, you see, it is a fixed potential, DC potential. This is a fixed, it is not variable, right. This is maybe AC ground, this you can set as a, this you consider as an AC ground, this may be connected to some DC potential. Okay. So, this potential will be fixed, it will not vary like this potential is varying. So, this is my signal, but this is my fixed bias. So, this is my driver and this is my, you can say, load transistor or bias transistor, whatever you can say. So, what is the job of this one? Can you tell me the Q2, what is the job of Q2? Q2, you see, if you have a BJT and if you add a fixed base emitter voltage, its collector current will be also fixed. If you have a constant voltage at the input, so this will be behaving like a current source. Okay. So, in our biasing we have seen several biasing technique, right. So, one biasing technique was fixed current biasing technique, current bias. So, this will ensure that this is getting always getting a collector current. This is defining that this IC. Okay. So, in this kind of circuit you always look for the input signal is connected to which terminal. So, that is your main driver. The other one is, you see, it is connected to a fixed potential. So, this is a DC circuit, DC input. So, this is a for biasing. Most of the time you will be seeing that it is used as a constant current source. So, this you can think of a current source having current I. Okay. All right. So, this emitter current is now, if you do the KCL at this node, it is I is equal to I plus I load. So, this is the current that is going to the load resistance. So, if this is your VI, can you tell me which kind of circuit this is? Output you are taking from the emitter terminal. So, this is common collector, which is also known as the emitter follower. Now, if emitter follows the input voltage, what will be your V0? Emitter follows the input voltage with a, can you recall? That was your input voltage. Emitter follower will be like this. So, that this gap is V, this drop is how much? VB. So, this is your VI, this is your V0 and this gap is VB. Can you recall? So, input is VI, you subtract VB, you arrive at which node? V0. So, you can tell that V0 is equal to Vi minus VB. So, you can also say this is a having a DC shift. Okay. So, what is the meaning? Whatever Vi, you subtract VB, VB how much roughly? 0.5, 0.7. So, you subtract that, you will get your V0. Clear? Next is, if we want to say that what is the maximum value of V0. So, this Vi can goes to maximum of, this is one KVL loop, another KVL loop is this, right. From the input side I can do one KVL, from the source also I can do one KVL. So, what is V0? VCC minus, what is this drop? VCE. Okay. So, another V0 is VCC minus VCE. So, when this will go to maximum? When this subtraction is minimum. So, when this subtraction is minimum? When this Q1 enters into saturation. In saturation, what is the VCE set? Roughly 0.2, 0.3. So, this max, this output will go to max value when this Q1 is at the point of entering saturation, and it will be VCC minus 0.2 or VCC minus 0.3. And if we want to discuss the minimum value of V0, so we are discussing that what could be the maximum value of V0 and what is the minimum value of V0. So, what could be the minimum value of V0? It should be defined by the lowest point. Lowest point is minus VCC, it will be above this VCE, right. You have to give this VCE drop, then you can reach this VCE. So, if you do the KVL from this loop, so it will be minus VCE plus VCE to saturation. Clear? So, this way we can define the maximum value and the minimum value. All right. Another way of defining this is that if suppose all the current I is flowing through this RL. So, this V0 mean can be minus I into RL. Okay. So, this is the lowest point, and this point the transistor is in saturation, right. Most of the time it is in linear or active, right. that is we want, and where it is getting flat, it is actually in saturation. This is Q1 in saturation, this is Q2 in saturation, okay. And this is another limit, that is the IRL, okay. So, we want our amplifier to operate in this zone. Why in this zone? What will happen if it cross this zone? That sine wave, its corresponding will be clipped, okay. So, suppose it is amplified, this will be clipped. If this is flat, what is the meaning? Input is falling, but output is not able to fall. In after this point, what is meaning? That input is increasing, but output is not able to increase, output is flat. So, that is the point you do not want, you want up to this, right. So, that if your sine wave is increasing, output is also following. Output can only follow up to which equation? Y is equal to mx. So, the region where this is followed, then your output V0 is a multiplication of Vi. So, where is that happening? From this point to this point. Okay. So, this is my linearity, and this is where it is getting flat. If it is getting flat, means my output will be clipped. Understood? So, if you want to use as a analog amplifier, your zone is this zone. If you want to use it as a switch, your zone is this flat saturation. This will be your logic 0, this will be your logic 1. So, you see the requirement is totally opposite. The digital circuit, you want the flat zone, you are not interested here, this is your forbidden zone, not defined, undefined. But in analog, your requirement is this is your forbidden. Why? Because your output will be no longer a sine wave, it will be clipped. Okay. So, please understand this very much basic, then you will be having no confusion that what is the requirement of a analog signal and what is the requirement of a digital signal, that you will can understand. All right. So, that we have discussed, that what is the characteristics of. So, can you tell me what is this characteristic? This characteristics is known as transfer characteristics, right? Transfer characteristics or input versus output characteristics. Where is your input? Vi. Where is your output? V0. So, x axis is your input, y axis is your output. So, whenever you are expecting an amplifier, you expect something like this kind of characteristics, right. Whenever you are expecting some inverter, you will be expecting something like this, right. Input is low, output is high, input is high, output is low. Okay. Okay. So, this is our Q2 is our biasing and Q1 is our main driver, and this driver you can understand that it is for 360 degree operation of the input sine wave, it is on, right. So, this falls in the category of class A. Now, these are the different plots. So, this is the plot for the V0. If we consider that full swing from output is going from minus VCC to plus VCC, it is able to deliver a full swing. So, minus VCC to plus VCC, full whatever the maximum possible range possible, you are getting that. Okay. Now, when your output is minus VCC and it is going to this VCC, when the total output is VCC, what is remaining for your VCE? Full is going to the output. So, VC is equal to 0. Okay. So, that time your VC is 0. All right. Now, your VC, your output is going to minus VCC. See, what is our maximum range from plus VCC to minus VCC? This is not 0 to VCC. So, our available range is twice VCC, right. So, VCC minus of minus VCC is equal to twice VCC. So, this maximum voltage, it will be allocated either to this or to this. Okay. So, my VC, this can go from 0 to twice VCC. Output, it can goes to minus VCC to plus VCC. So, what is the range? Twice VCC. So, peak to peak, what is the peak to peak? Peak to peak maximum possible is twice VCC. So, this twice VCC, either it will go to output or it will go to VC. These are two options, right. What is my KVL saying? KVL is saying this path, this output will be through this. Okay. So, this twice VCC, either it will come to this or to this. Okay. So, again my VCs can go from 0 to twice VCC. This output is going to minus VCC to VCC, but when it is VCC it goes to 0. So, it go from 0 to twice VCC. Okay. Similarly, for IC, I am already giving a, initially it would go from minus I to plus I. I have added a DC. So, now its minimum point is 0 to twice I. If we do not have the DC added, it should go from 0 to minus I to I. But now what I am doing? I have added a this much DC. So, this IC, its voltage it can go from 0 to twice I. Okay. And this is the power dissipations. Maximum power dissipations is VC into I. Okay. All right. So, let us define the power efficiency. The power efficiency is the power delivered to the load divided by the power supplied. How much power I am providing to the load? What is our load resistance? RL. So, we will be calculating I square RL, I square R or V square by R. Okay. So, we can derive this PL. We have two equations, one is I square R or V square by R. Now, this V square, what is given to us? Peak value. Peak means maximum. So, we should assume the average power. So, average voltage is V0 by root 2. If peak value is given, so average is, this is my peak, this peak is peak. This is RMS. Okay. Okay. So, we will be taking RMS V 0 by root 2 and this is V square by RL. Okay. So, this is our load. Now, what is the supply? I have two supply, one is VCC, another is minus VCC. So, total power is twice VCC into I. So, what I will do? I will do PL by PS is equal to V 0 square by twice RL into twice VCC into I is equal to V 0 by 4 IRL into V 0 by VCC. Okay. Now, you assume that what could be the maximum efficiency, for which case this will be maximum if V 0 by IRL and V 0 by VCC these terms are 1. So, suppose we are assuming that maximum V 0 is equal to VCC. So, this term will be cancelled and let us consider that V 0 is equal to IRL. So, maximum we are considering V 0 is equal to IRL is equal to VCC. So, what will be zeta max? 1 by 4. 1 by 4 means how much percentage? 25%. So, what is the meaning? 1/4 of the power is actually delivered to the output, rest of the power are dissipated as wasted as a heat. So, you see, okay, we have understood that this amplifier, this is operating for full sine wave, but as it is operating for more time, the heat dissipation is also more and we arrive at a efficiency of maximum. It is even less than that, right? We have considered the maximum. So, you can understand that this is very much, efficiency is very poor. Okay. So, let us move to class B. Why we are moving to class B? Because we found that class A efficiency is very poor. How much? Only 25%. So, actual efficiency is even less than that. So, this you see, can you see the difference of the previous circuit and this circuit? There is no DC, only the signal, this Vi, this is the signal only. In analog amplifier, what you saw, that there will be some potential divider bias, current source bias, no biasing. Okay. So, you see, I am having, let us make it simple. Let us see, if it is above 0, this will be on, if it is less than 0, this will be on. This is complementary, right? One is NPN and another is PNP. So, they will be, their on criteria are just complementary. So, you just make it simple. You think that if it is above 0, Qn will be on, if it is below 0, Qp will be on. Okay. So, when Qn is on, the direction of current flow is this, right. So, this voltage will be building up. When Qp is on, the direction of current flow is this. So, direction in RL is opposite. So, it will be in opposite direction. Clear? What we are doing? You see, in this direction, when this is driving, this is pushing the current into the load. This transistor is pushing the current into the load. So, this load voltage is building up, V is equal to IRL positive. Now, input goes to 0 less than 0, this transistor goes off, this path is disconnected and this path is now connected. Now, you see this path is, it is sinking current. So, this is a source, this is a sink. So, now the direction is in opposite direction. So, voltage build up at the output, it will be minus I into R. So, it is in the next half, means previous case it was above 0, it will be below 0. So, negative. So, that is the way I get a output, but you see the region of operation is only 180 degree for each transistor. For this positive 180 degree, which one is operating? Qn. For negative 180 degree, which one is operating? Qp. Previous case it was not so. Previous case this was operating for full, even for positive, even for negative, this was operating. This was also operating, but this is not a driver, this is a fixed bias. Clear? You understood the difference between that operation of two. In this case, one single transistor is operating for half of the sine wave. Okay. And another thing is that there is no DC component, only the if signal is above the base emitter voltage, right. If this Vi goes above the base emitter voltage of Qn, Qn will be on. If this Vi goes below the emitter base voltage of Qp, Qp will be on. So, ideally we assume that, okay, let us assume that this transistor is on at 0, idealistic situation, but real situation will be 0.5 to minus 0.5, though this zone you can define like a dead band, right. This is my dead band. During this dead band, both of the transistor are off. So, what will happen to the load voltage? If both of the transistor is off, who will be delivering my current to the load? This path is also disconnected, this path is also disconnected. My output power is 0, clear. So, during 0, this is my input full sine wave, but my output is something like that. So, I am having a distortion at 0 crossover. So, this is the main problem of class B. Okay. Class B have some advantage. What is the advantage? Half of the time I am making it off. Okay. So, the loss, power dissipation loss will be reduced. Okay. We will be seeing that in the equation. So, again our load power is V square by twice RL. Now, see, as I am providing only half of the time one transistor is on. So, my power supplies is average power from the two power supply is the current into VCC, right. PS was this I into VCC. Now, this I is my peak power by, I have to find the average power, right. This is my average supply by RL. So, this is my current into VCC, clear, because I am taking average of this. It was not that full sine wave, only the half, right. So, if we calculate this, we will get the average current. So, average current is this much portion. So, I have to multiply it with 2 because this is for both of the case. So, my power supply is, in previous case what was my power supply? Twice VCC into I, but in this case it is not twice VCC into I. In this case this I we are defining like twice V0 peak by pi RL into VCC. So, we are dividing with pi to get the average. Okay. So, you understand that my power supply is now reduced. Previous case I was delivering for full sine wave, I was delivering to this as well as this. This transistor I was delivering power for half cycle and the other half cycle. This transistor also I was delivering for this positive half cycle as well as the negative half cycle. But in this case I am delivering for positive half cycle only to this, not to that, and negative half cycle I am delivering only to this, not to that. So, already my power supply that I am delivering, that is reduced. Previous case I need to deliver power to both of the transistor, both of the cycle, but in this case I need to deliver power for only one transistor at one cycle. So, my supply is already reduced by this amount. So, that will be reflected in my efficiency. So, if you want to find the efficiency, that is this PL divided by PS, that is half V square by RL divided by twice V by pi RL into VCC is equal to pi by 4 V0 by VCC. Now, let us consider that V0 is equal to VCC. So, whatever maximum efficiency you are getting, pi by 4, calculate it percentage wise, roughly 78.5%. Previously it was less than 25%, you have improved up to 78.5. How you did that? By turning the transistor off for half of the cycle. Now, you see, if we plot the power versus the output, then I will be having a point where the power is maximum, right. One point is where the efficiency is maximum and another point will be there where the power dissipation is maximum. Okay. May not be that highest power dissipation point may not be your highest efficiency point. Okay. So, maximum power dissipation point is where efficiency is minimum, less than that, your maximum efficiency is 78.5%, but at the point of maximum power your efficiency is reduced to 50%. Okay. So, that is the calculation, that our power dissipations, if we want to find the maximum, where it will be maximum, that is for the input when this output is twice VCC by pi, but where the efficiency will be maximum, that is V0 is equal to VCC, but where the power will be maximum, that point is V0 is equal to twice VCC by pi. That we can do the maths and can check that. So, I will be discussing that in next class. Okay. So, you just remember this plot, that it is not that where the power dissipation is maximum, the efficiency is also maximum. Efficiency is maximum at some other point. So, at which output it is maximum efficiency, that is where V0 is equal to VCC, and that time our efficiency is 78.5%. And when the V0 is equal to twice VCC by pi, my power dissipation is maximum. Okay. So, that is our discussion on class A and class B power amplifier. So, in next class we will be checking how we can overcome the problem of class B, that in class AB. Okay.